Hello everyone, I am Nakshatra Mantraprabha VG, a final year student from Avinashilingam Institute. I did my internship at Emertex and built something like a mini EV dashboard, the kind you would see in a real electric car. Using a small microcontroller called STM32, it also has a basic safety system like the collision warning you see in the modern cars. Let me walk you through what I built and then I will show a live demo as well. So basically, I have made a small computer chip which acts like the brain of the electric car. It tracks things like speed, battery, and temperature. And it also has three distance sensor, like ones in the car that beeps when you're too close to something. This whole thing runs on one small board. Not real car needed here. Everything is simulated. So the tools and development environment that I've used in this projects are STM32 Cube IDE. This is the place where I wrote the code. Pixum Lab. It pretends to be the actual hardware, so I didn't need any real wires or sensors here. Python. So Python is used to create a nice dashboard screen to show speed, battery, and all of that visually. VSPE and Teraterm. This is just a simple window where I can type commands and see message from the chip. So coming to the system architecture, this is the flow of our project. Starting from sensors, it reads the distance and pedal position. EV control, it is the car brain which indicates the speed, battery, torque. ADAS, it checks for danger like something too close in front. Fault, it checks if something is going wrong like overheating. You what, it sends everything to my computer screen. They all check with each other 10 to 100 times every second, so everything updates here almost instantly. So coming to the pin configuration, so we are using potentiometer here. So the pin range for it ranges from PA0 to PA3. So PA0 indicates the accelerated pedal, PA1 indicates the brake pedal, PA2 indicates the state of charge, and PA3 indicates the motor temperature. And for the digital input output, we are using three ultrasonic sensor here. So for the front ultrasonic sensor, PB0 and PB1 pins are used. 0 is for the trigger pin, 1 is for the echo pin. Similarly, for left and right ultrasonic sensor, PB2 and 3 are used, and for the right, PB4 and 5 are used. So we are also using 4 LEDs here. PB8 LEDs for the collision warning, PB9 LEDs for the blind spot left, PB10 LEDs for the blind spot right, and PB11 LEDs for the LED which indicates the fault active. And these are the formula which are used for conversion here. So how the distance sensor works here, which is ultrasonic sensor. So the ultrasonic sensor sends out a short sound pulse like a mini shout and waits for the echo to bounce back. The longer it takes to come back, the farther the object is. So the formula is time taken into speed of sound divided by 2. We divide by 2 because the sound travels to the object and back. We only want the one way distance here. The sensor can measure between 2 centimeter and to 400 centimeter. If nothing is nearby, it just shows 400, meaning nothing is being detected. So coming to the timers, we are using three timers here. One is used to update the car speed and battery every 10 millisecond, basically instantly. Another checks for the distance and danger warning every 100 milliseconds, 10 times a second. And third one is just to use it to measure how long the sound echo takes, like the stopwatch. And how the car speeds up and slow downs. When you press the accelerator, torque, which is like the push force, increases. There are three driving modes: eco, normal, sport. So in eco mode is a gentle mode. About 60% of the power is being used here. Normal uses regular power and sport mode is stronger. About 130% of power is used here. And we also have 5 states here: park, ready, driving, regeneration, and fault. So the car goes from parked state to ready state when the acceleration pedal is being pressed, and from ready to driving, it goes automatically. And from driving to regeneration, it goes when the brake pedal is being pressed above the threshold. And fault state goes whenever any kind of fault is detected in the above mentioned states. So when you press the brake, it doesn't just stop the car, it also puts a light energy back into the battery. That's called the regenerative braking. Same ideas as in the real electric cars. So battery and range, the battery percentage drops based on how much power the motor is using. If the car isn't moving but the motor is working hard, the battery still drains a little, just like in the real life. Running the AC in the parked car still uses battery, right? Similarly, here it also uses battery. Range. How many more kilometer you can go was calculated from how much battery is left divided by how much energy the car user uses per kilometer. Eco mode uses less energy, so range is longer in eco mode. Coming to the ADAS part, so this is the safety part. Two things are checked here. How close is the object in front and how fast are we going and how soon would we hit it. The second one is called TTC, which is time to collision. It means how many seconds until we crash if nothing changes. The formula for TTC is distance divided by speed. If the object is very close or a TTC is very short, we get a warning. If it's even closer or more urgent, we get a critical alert. Roughly under 50 centimeter or 3 seconds, warning has been generated. Under 20 centimeter or 1.5 second, critical is being generated. And coming to the blind spot and other checks, there are also called blind spot detection. If something is within 30 centimeter on the left or right and we are driving faster than the 20 kilometer per hour, it warns us. It only checks this while actually in the driving state, not while in the parking or just it is just like the real car here. There is also a overspeed check. If we go above 120 km per hour, it gives a gentle warning. So coming to the fault detection, this part watches for problems such as a motor getting too heat, battery getting too low, and a serious crash warnings. If any of this happen, the system automatically stops the motor for safety. It doesn't wait for anyone to press a button. Once things go back to normal, it can also reset itself back to the safe starting state. So you what a command shell? It is the talking to the computer. So I built a simple command system. I can type things like status, which shows the everything right now. Mode sport, switch driving mode. Obstacle 15 pretends there is something 15 centimeter away. Fault inject motor, pretend the motor is overheating. This let me test everything without needing real sensors nearby. The dashboard. So all this data, speed, battery, distance warnings get sent to my computer and I built a Python dashboard that shows it visually. Like a real car dashboard with a speed needle, a battery bar and a little bird's eye view showing where objects are around the car. So the key learnings throughout this internship is basically I learned how to make a chip to do many things at once fast using timers, read sensors and turn raw numbers into real distance and speed, build a safety system that reacts on its own to danger, connect all of this to a nice virtual screen on my computer. That's the whole project in the nutshell. So now let's see the demo. Starting with the STM32 Cube IDE, as we can see here, I have created a separate project file like EV dash, and I also included all the header files and source files here for everything, like every components that we have used here, like ultrasonic sensor, fault, EV control, ADAS. So for everything, have separately created the header file and source file, and we have included all this in the main.c. So we have included it in the main.c as well as we have also initialized here. So when coming to the input output configuration, we have the pin configuration for all the components that we have used. We have ADCs, input output pins, and we have ultrasonic input output pins and UART communication pin and etc. And we have also included the three timers here And for connectivity, we are using the universal synchronous, asynchronous receiver and transmitter. And we also initialize the clock configuration. We have selected here the HSC, which is the external clock, and we have selected the multiplexer and prescaler clock. Everything we have configured here. So after making these changes, when we save this, it automatically will generate the main.c code here. Here we have just included the header and source file. After that, and when we click here and build our project, we can able to see the error and warning in this code. Here we have zero error and warning. After this, we'll go to the Pixum lab. So in Pixum lab, we have selected the microcontroller that we have needed here, which is the STM32F 103C8T6, and we have set the clock frequency. And in file, when we give the load binary, we can able to load this EV dash as a binary file. After this, we'll open the spare part. In spare components, we are connected the potentiometer, ultrasonic sensor and LEDs here. And this is the virtual terminal throughout which we can detect the fault. For example, when the motor temperature is high, we will have the yellow LED blinking, but it will take some time here. As we can see, the yellow LED is blinking. In the virtual terminal also, we will be getting the fault as 01. Like we can see, we can getting the fault as 01. So in the code, we have coded that when the fault so in the motor temperature, we'll have 01. If the battery is critically low, we'll have the 02. And when the collision is critical, we'll have 04. So this is what we have coded. So according to that, we can able to see the outputs here. So this is about when we lower the distance between the obstacle, which is below 30 centimeter. We can able to see the LED blinking here, but it's kind of the value reflecting in the virtual terminal, and the LED is kind of slow here. So after this, we have the VSP PE. So here we have selected the virtual pair between a COM1 and COM4. So in the Pixum lab, we have selected the COM as COM4, as we can see here, and in the Terraterm app, we have selected the COM1. So the all the values that we can able to see in the Pixum lab are can also be able to see in the which COM1 also in the Terraterm, but unfortunately I can't able to type help here. So we can able to see all these things. And when we open the command prompt, as you can see here, I have loaded the location of my ev dash file, and I also opened the ev dash python dashboard. So after coding this in the command prompt, directly we will have this window, which is the ev dash dashboard. Here we can able to see the all the parameters that we have coded virtually. So this is the ADAS bird view, and this is the front vehicle, and this is our car vehicle. So these are the EV parameters: torque, acceleration, brake, motor temperature, alarm, fault, signal, and this is the speed history. And when we increase the speed in the potentiometer, PA0 terminal, we can able to see that in the ADAS dashboard. But here it's taking little bit of time to load here, but it will be loading here after a few minutes. So this is our dashboard that we have implemented. So when the right or left vehicle, when the blind spot LR or is below the 30 centimeter, we'll have the advisory alarm. When it is below the 20 centimeter, we'll have the critical alarm here. As we can see the vehicle here in the right. When this distance gets below 20 or 30, we can able to see the advisory alarm here. So this is the overall project that we have implemented during this internship. So I would like to thank my internship team, that is Emertex team, for constantly guiding me throughout this project. And I also like to thank our mentor Jayalakshmi ma'am, who has been our constant support throughout this internship, and looking forward to do many more internship in the Emertex as well. So I thank everyone who's watching this video, and this is the overall project that we have implemented. Thank you.